Gradation in properties of group 17, that means halogen family. Okay, first point, electronegativity decreases from fluorine to iodine. Electronegativity decreases from fluorine to iodine. Second point, density, melting point and boiling point increases. Density, melting point and boiling point. Density, melting point and boiling points increases from fluorine to iodine. Okay. Third point, color of these halogens depends with the rise of atomic number. Okay, fluorine is pale yellow. And chlorine is greenish yellow. Chlorine is greenish yellow. Chlorine is greenish yellow, and bromine is reddish brown. And iodine is deep violet. Okay, deep violet. Okay. Color of these halogens depends with the rise of atomic number. Okay. Fourth point, reactivity decreases with rise in atomic number. Okay, reactivity decreases with rise in atomic number. Okay, reactivity decreases with rise in atomic number. Okay, the great reactivity of fluorine stems from the low energy from fluorine bond. The fluorine bond is weak due to repulsion between non-bonding electrons. Fifth point, reactivity with water decreases on moving down the group. Reactivity with water decreases on moving down the group. Okay. And fluorine reacts with water giving oxygen and ozone. Chlorine reacts with water slowly giving HCl and HCl. Bromine shows very feeble reaction. Iodine is sparingly soluble in water. Okay. Fluorine reacts with water giving fluorine reacts with water giving oxygen and ozone. Chlorine reacts with water slowly. Giving HCl and HClO. HClO. Bromine shows very feeble reaction. very feeble reaction, chlorine, very feeble reaction. Iodine is sparingly, iodine is sparingly soluble in water, okay. Anomalous property of fluorine. Anomalous abnormal property of fluorine, okay. Anomalous property of fluorine, okay. Fluorine is the first member of the halogen family. Okay. Most of the properties of fluorine resemble with other halogens, but it exhibits anomalous behavior in some respect with the other halogens. Anomalous behavior of fluorine arises due to anomalous behavior of fluorine arises due to first point, small size of fluorine atom. Small size of fluorine atom. Small size of fluorine atom. Second point, high electronegativity. Third point, absence of d orbitals in its configuration. Absence of d orbital in its configuration. Absence of d orbital in its configuration. Fourth point, high oxidizing power. Fifth point, weakness of fluorine bond. Weakness of fluorine bond. And sixth point, inability to expand its octet. Inability to expand its octet. Okay. And seventh point, high value of first ionization potential. High value of first ionization potential of fluorine in comparison to other halogens, okay. Anomalous behavior of fluorine, okay. First point, small size of fluorine atom, high electronegativity, and absence of d orbitals in its configuration, and high oxidizing power, weakness of fluorine bond, inability to expand its octet, and high value of first ionization potential of fluorine in comparison to other halogens, okay. Next heading, difference between fluorine and others. Difference between fluorine and others, okay. Difference difference between fluorine and others. Okay. First member of the group differs in property from the rest due to small radius and high electronegativity, absence of d orbital in its configuration, high oxidizing power. Fluorine has property different from chlorine, bromine and iodine. First point. Fluorine shows oxidation state -1 and 0 only. Fluorine shows oxidation state. Fluorine shows oxidation state. Fluorine shows oxidation state of -1 and 0 only. Okay. It does not show positive oxidation state. It does not show positive oxidation state. Second point. Fluorine is not prepared by the electrolysis of anhydrous. Fluorine is not prepared by the electrolysis of anhydrous of hydrogen HF because it is non-conducting. Third point. Fluorine is not prepared by the electrolysis of aqueous. Fluorine is not prepared by the electrolysis of fluorine is not prepared by electrolysis. Fluorine is not prepared by electrolysis of aqueous. Okay. Fluorine is not prepared by electrolysis of aqueous NaF because fluorine reacts to form HF and O2. Fluorine is not prepared by the electrolysis of aqueous NaF because F2 reacts to form hydrogen fluoride and oxygen. Okay. Fourth point. HF shows hydrogen bonding. HCl, HBr, HI do not. Okay. Fifth point. HF is a weakest acid. HF is a weakest acid. Okay. Weakest acid and weakest reducing agent and weakest reducing agent among all HFs. among all HX, okay? Thus HF is not a strong acid like HCl, HBr and HI. 6 point. Fluorine ion forms HF2 negative due to hydrogen bonding. Hydrogen bonding, okay? Hydrogen bonding. HCl2 negative is not known. Okay? Not known. HCl negative is not known. Okay? Next point, 7 point. AgF is soluble in water. Silver fluoride, AgF is soluble. AgF is soluble in water. Okay? AgCl is not insoluble. AgCl is insoluble. AgCl is insoluble. Okay? IX 9 point. 8 point. Point number 8. Okay? CaF2 is insoluble. CaF2 is insoluble. Otherwise, CaCl2 is soluble. Okay? 9 point. Fluorine does not form polyhalide. Fluorine does not form polyhalide. Fluorine does not form polyhalide. Other form ICl2 negative, I3 negative. Okay? Next point, 10 point. SF6 sulfur hexafluoride is formed. Okay? SF6 is formed and not HCl6 due to large size. Of chlorine. Okay? 6 point 6. With some metals, fluorine form electrovalent compounds. With some metals, fluorine forms electrovalent compounds. Electrovalent compound. Example: AlF3, but the compounds with chlorine. Example: AlCl3 is covalent. Okay, and 12 point. In the compound like sulfur hexafluoride, arsenic pentafluoride, and iodic heptafluoride, the elements sulfur, arsenic, iodine, exhibit their maximum valencies, but such is not the case with other halides. Okay? Next point. In the compounds like SF6 and IF7, the elements SF6, IF7 and AHF5, okay? The elements sulfur, arsenic and iodine exhibit, their maximum valency, but such is not the case. Such is not the case. Such is not the case with other halides. Case with other halides. Okay. Example: SCl4, AlCl3, ICl3, etc. Okay. And the next point, 14 point. Point 14, 1 minute. 13 point. Point 30. That means S equal I 13 point. Chlorine does not give oxide salt with sodium hydroxide, but the other gives. Okay? Chlorine does not give oxy salt with NaOH, but others give. Okay? 2NaOH plus 2F2. Okay? Cold and dilute. That is 2NaF plus F2O plus H2O. 4NaOH plus 2F2. That is hot and concentrated. 4NaF, sodium chloride, plus 2H2O plus O2. 2NaOH plus Cl2. Cold and dilute. That makes NaClO plus NaCl plus H2O. Okay? 6NaOH plus 3Cl2. That is hot and concentrated. NaClO3 plus 5NaCl plus 3H2O. Okay? And 14 point. Chlorine can directly combine with carbon. Chlorine can directly combine with carbon and carbon. Chlorine can directly combine with carbon and silicon, while other halogens cannot. Okay? Because CH2F2, that makes CF4, 2F2. Okay? Silicon plus F2, that makes SiF4, 2 to 4 fluorine. Okay? 15 point. Reaction of fluorine with water is explosive, and the mixture of oxygen and ozone formed. Okay? Ozone formed. Okay? Then 2F2 plus 2H2O. That makes 2H2F2 plus O2. Okay? And 3F2 plus 3H2O. That makes 3H2F2 plus O3. Okay? And next reaction of fluorine with water is explosive and mixture of oxygen and ozone is formed. Okay. Next, other halogens also react with water, but the product is the mixture of halide and hypohalide. Chlorine plus H2O, that makes HCl plus HClO, and X2 plus H2O, that makes HX plus HXO. Next reading, charge of similarities between fluorine and oxygen. Charge of similarities between fluorine and oxygen. Okay. Fluorine and oxygen show similarities due to following reasons. First point, the atomic and ionic radii of both are approximately same. The atomic and ionic radii of both are approximately same. Are both approximately same. The atomic and ionic radii are both are approximately same. Okay. Third point, both possesses non-availability of vacant D. Both possesses non-availability both possesses non-availability of vacant D orbitals in their electronic configuration. Okay, electronic configuration. Okay, both possesses non-availability of vacant d orbitals in their electronic configuration. Okay, similarities between fluorine and oxygen. Okay, first point, both are very reactive and form stable compounds. Both are very reactive and form stable compounds. Okay. Second point, the hydrides of both H2O and HF exist as associated molecules. Okay, they are associated due to strong hydrogen bonding. These are associated due to strong hydrogen bonding. strong hydrogen bonding, strong hydrogen bonding. Okay. Third point. H2O and HF are good solvent. H2O and HF. H2O and HF are good solvent. Good solvent and possesses high boiling point in comparison to their group hydrides. Okay, hydrides. Fourth point. HF is closer to water. HF is closer to water than any other halogen acids. Okay. Both of HF and H2O are weak acids. Weak acid. Okay. Fifth point. The range of fluidity. The range of fluidity of H2O and HF are similar. Okay. Sixth point. Heat of formation of some fluorides are closer to those of the corresponding oxides, but not those of chlorides. Bromide are hydrides. The heat of formation of H2O is 68.4 kilocalorie, HF 64.2 kilocalorie, and HCl 22.0 kilocalorie. Okay. 7th point. Both combine directly with carbon. Both combine directly with carbon. C plus O2, that makes CO2, and C plus 2F2, that make CF4. Okay. And 8th point. Both combine with sulfur and form stable compounds. Both combine with sulfur. Both combine with sulfur. Both combine with sulfur and form. Both combine with sulfur. Both combine with sulfur and form stable compounds. like SF6 and SO3 with maximum covalency. Okay. Both combine with sulfur and form stable compounds like sulfur hexafluoride and sulfur trioxide with maximum covalency. Okay. Next heading, maximum covalency 6. Next heading, hydrides of boron. Okay. Hydrides of boron. Boron does not react with hydrogen directly. But several hydrides are known which are formed by indirect method. It may be noted that BH3 is not known. BH3 is not known. BH3 is not known. It is electron deficient and demineralized to B2S6. Okay. Hydrides of boron having general formula. Hydrides of boron. Hydrides of boron having general formula. Hydrides of boron having general formula BnHn plus 4 and BnHn plus 6 are known. Okay. Boron hydride with general formula. BnHn plus 4 are called boranes. By analogy with the alkanes. By analogy with the alkanes. Okay. First point. BnHn plus 4 where n equal to 2, 5, 6, 8, 10. Okay. Borons are very stable and possesses high melting points. Borons are very stable and possesses high melting points. Okay. Second point. BnHn plus 6 is that n equal to 4, 5, 6, 8, 9, 10. Thus boron hydrides with general formula. BnHn plus 6 are called hydroboranes. These are unstable. And possesses low melting point. Unstable and possesses low melting point. Okay. BnHn plus 4 boranes and BnHn plus 6 hydroboranes. Okay. B3H6 diborane. B5H9 pentaborane and B6H10 hexaborane. Okay. Hexaborane 12. Hexaborane 10. Okay. And B8H12 octaborane. Octaborane 12. And B10H14 decaborane. Decaborane 14. Okay. And B4H10 tetraborane. B5H11 pentaborane 11. Pentaborane 11. and B6H12 hexaborane 12, hexaborane 12, and B8H14 octaborane 14, octaborane 14, and B9H15 nonaborane 15, boron 15, and B10H16 decaborane 16, boron 16, okay, decaborane 16, okay. The number of hydrogen atoms is included in name of boron hydrides. For example, hexaborane with 10 and 12 hydrogen atoms are named as hexaborane 10 and hexaborane 12 respectively, okay. When boride is treated with dilute acid, mixture of borans is obtained. The chief constituent in the mixture is B4H10 and B2H6 is in traces, okay. As an example, Mg3B2 plus 6HCl that make B2H6 and plus 3MgCl2 and 2Mg3B2 plus 12HCl that make B4H10 plus 6MgCl2 plus hydrogen, okay. The mixture of hydrides condense to a liquid from which they are separated from one another by fractional distillation, okay. Diborane or boroethane B2H6, okay. Diborane or boroethane B2H6. Diborane B2H6 is also called boroethane, okay. Preparation of diborane, okay. Diborane is prepared by following method. First point, lithium aluminum hydride is treated with boron trichloride in anhydrous diethyl, okay. Then 3LiAlH4 plus 4BCl3 that makes 3LiCl plus 3AlCl3 plus 2B2H6, okay. 99.4% yield, okay. And the second point, boron trifluoride is treated with sodium borohydride in the presence of dimethyl ether, 3 sodium NaBH4 plus 4BF3 that make 3 NaBF4 plus 2B2H6. That is 99.99% yield, 99% yield, okay. And the third point, okay. It is also prepared by reduction of boron trihalide with lithium or sodium hydride, okay. Then 2BCl3 plus 6NaH that make 197 degrees Celsius and B2H6 plus 6NaCl, okay. BCl3 plus 6NaOH at 197 degrees Celsius, B2H6 plus 6NaCl, and 2BF3 plus 6LiH that make B2H6 plus 6LiF and 2BF3 plus 6NaH at 180 degrees Celsius temperature. B2H6 plus 6NaF. And 4 point. When boron trioxide is reduced with aluminum and hydrogen, diborane is formed. Okay, B2O3 plus 3H2 plus 2Al at 750 atm pressure, 150 degrees Celsius, that make B2H6 plus Al2O3. Okay, and the physical property of diborane are boroethane. Okay, physical property of diborane are boroethane. Diborane is a colorless gas. Physical property: diborane is a colorless gas. It is fairly stable at 25 degrees Celsius. Fairly stable at 25 degrees Celsius. Thus, it is stable at lower temperature and in the absence of humidity. Okay. Thus, it is chemical properties of diborane. Okay. Chemical properties of diborane B2H6. Okay. First point. It is highly reactive. It is highly reactive. Okay. It is highly reactive. Okay. Second point. It catches fire spontaneously in air and explodes with dioxygens. Okay. B2H6 plus 3O2, that make 2B2O3 plus 3H2O plus Q. That means delta H equal to 2265. Okay. Kilojoule per mole. Okay. Then third point. It reacts with a sodium amalgam. To form an addition compounds Na2B2H6 plus a sodium amalgam, that make Na2B2H6. Okay. B2H6. Okay. Fourth point. It is instantaneously hydrolyzed by water. B2H6 plus 6H2O, that make 2H3BO3 plus 6H2. Okay. Fifth point. It is also hydrolyzed by alkali. B2H6 plus 6H2O, that make 2H3BO3 plus 6H2. Okay. And 2H3BO3 plus 2NaOH, that make 2NaBO2 plus 4H2O. Okay. That make B2H6 plus 2NaOH plus 2H2O, that make 2NaBO2 plus 4H2O. Okay? Sorry, B2H6 plus 2NaOH plus 2H2O, that make 2NaBO2 plus 6H2 plus 6H2. Okay? Next, 6 point. It is electron deficient and so form addition compound. Okay? It is electron deficient. It is electron deficient and show forms addition compounds and so far addition compounds. Okay? Then first point, A, with carbon monoxide it forms 2BH3CO. B2H6 plus carbon monoxide, that make 2H3B. Okay? C triple bond O. B point. With PF3 phosphine it forms 2BH3PF3. Okay? B2H6 plus 2PF3, that makes 2H3B PF3. C point. With excess of ammonia at low temperature is forms 2BH3NH3. B2H6 plus 2NH3 ammonia, that react, and after reaction this make 2H3B NH3. Okay? D point. With excess of ammonia at higher temperature it forms BN. B2H6 plus 2NH3 at higher temperature B2H6 plus 2NH3, that make 2H3B NH3. After higher temperature H3B is also converted in BN plus 3H2. Okay? E point. When B2H6 and NH3 ammonia in the ratio 1:2 are heated, B3N3H6 borazole or borazine or inorganic benzene is formed. Okay? B2H6 plus 2NH3, that make B2H6 2NH3, 3B2H6 2NH3 at a higher temperature it also converted in 2B3N3H6 plus 3H2. Okay? And B3N3H6 is isoelectronic with isoelectronic with C6H6 benzene. Okay? 7 point. With hydrochloric acid diborane forms B2H5Cl. Okay? B2H5Cl. Okay? B2H6 plus HCl hydrochloric acid, that make B2H5Cl plus H2. Okay? eighth point. With chlorine diborane forms BCl3. Okay. Then B2H6 plus 6Cl2. 6Cl2, that make 2BCl3 plus 6HCl. Okay. And the next point number 9. Point number 9. Okay. Point number 9. IX. Point number 9. IX. With alcohol B2H6 forms alkyl borate. Alkyl borate B2H6 plus 6CH3OH. That make 2BOCH3 whole thrice plus 6H2. 6H2. Okay. Methyl borate. Methyl borate. Methyl borate. Okay. 10 point. Upon heating with bromine, diborane forms bromodiborane. Okay. Then B2H6 plus Br2, that make B2H5Br plus HBr. Okay. 11 point. Hydroboration. Hydroboration. Okay. Diborane reacts with alkene or alkynes in dry ether to form alkyl or alkenyl borane as useful intermediates which are used in organic system. Then B2H6 hydroboration. Diborane reacts with alkenes. Diborane reacts with alkene or alkynes in dry ether to form alkyl or alkenyl borane as useful intermediates which are used in organic synthesis. Okay. B2H6 plus 6RCH double bond CHR, that make 2BRCH2CH2 whole thrice. Okay. B2H6 plus 6RC triple bond R 2BRC double bond CHR whole thrice. BCH2CH2R whole thrice plus H2O2, that make 3RCH2CH2OH plus H3BO3. Okay. At 1 degree primary alcohol. 1 degree primary alcohol. 1 degree primary alcohol. Okay. Usage of diborane. Usage of diborane. Usage of diborane. Okay. Usage of diborane. First point. As a rocket fuel. As a rocket fuel. As a rocket fuel. Second point. As a catalyst in polymerization reactions. As a catalyst in polymerization reactions. Okay. Third point. As a reducing agent in organic reactions. As a reducing agent in organic reaction. Okay. Fourth point, for the preparation of higher borans, for the preparation for the preparation of higher borans. Okay. Fifth point, for the preparation of boron, for the preparation for the preparation of boron, for the preparation of boron nitride Bn, boron halide BX3, and metal boron hydrides, metal boron hydrides. Example, LiBH4 into NaBH4. Okay. 6 point. For preparation of inorganic benzene. B3N3H6. And 7 point. For the preparation of alkyl borates. For the preparation of alkyl borates, BOR whole thrice. Okay. Structure of diborane. Next, structure of diborane. Okay. 1 minute. Structure of diborane. Okay. Structure of diborane. Okay. The molecular formula of diborane B2H6. The molecular formula of diborane is B2H6, which is similar to the formula of ethane, ethane C2H6. Therefore, the structure of B2H6 should be similar to C2H6. Ethane is a stable molecule and has 14 valence electron. Okay. There are 7 bonds present in C2H6 molecule, but in case of B2H6 molecule, the total number of valence electron 3 plus 3 plus 1 multiplied 6 is 12. But the number of bonds is 7, which requires 14 valence electrons. Thus, there are 2 less electrons in B2H6. Hence, B2H6 remains electron deficient compound. Okay. Boron. Okay. 1 hydrogen combined with 1 hydrogen, and here combined with 1 hydrogen. 3 hydrogens, and combined with 1 hydrogen, and combined with 1 hydrogen, and combined with 1 hydrogen. This is diborane. And boron, hydrogen, okay. Diborane, okay. And ethane, carbon, 1, 2, 3, 4. Okay. 1 hydrogen, 1 2, 3, 4. 1 hydrogen, 1 hydrogen. This is ethane. Okay. From the above structure of diborane, it is clear that there is no bond exist between 2 boron. boron, two boron atom due to two boron atom due to lack of one pair of electrons. Although there exists a single bond between carbon-carbon in C2H6, Sagweed suggested that diborane has Sagweed suggested that diborane has ethane-like structure with a difference that two hydrogen atoms in B2H6 are held by one electron bond. These structures are not supported by experimental data and due to which rejected. Okay? On the basis of electron diffraction, Hedberg and Schoemaker proposed a hydrogen bridge structure. This structure is later unjustified by infrared spectroscopic technique. Roman spectra and NMR spectra above studies show that 4-terminal BH bond length is 1.19 angstrom, while the bridging bond length boron hydrogen is 1.33 angstrom. Electron diffraction results indicate the structure shown. You can show this boron, hydrogen, boron. The angle is 122.7 degree, and this is hydrogen, and the bond length, boron hydrogen bond length 1.19 angstrom, and hydrogen. This is hydrogen, this is boron. Okay, and boron, hydrogen, boron, and this is boron, hydrogen, boron. Okay, and the bond angle boron hydrogen boron bond angle is 100 degrees Celsius, and hydrogen bond angle is hydrogen boron bond angle is 97 degrees Celsius, and the bond distance between boron to boron is 1.77 angstrom. 1.77 angstrom. Okay, bridge structure of diborane. This is the bridge structure of diborane. Bridge structure of diborane. In bridge structure of diborane, the two boron atom and 4-terminal hydrogen atom. Two boron atom and 4-terminal hydrogen atom. 1, 2, 3, 4 hydrogen atoms are coplanar, while two bridging hydrogen atoms are perpendicular to the plane. Following facts support the bridge structure of diborane. First point A. The two bridge hydrogen atoms are in plane perpendicular to the rest of the molecules and prevent the rotation between the two boron atoms. Okay? Specific heat measurements confirm that rotation is hindered. Specific heat measurement confirm that rotation is hindered. Okay? 4 of the hydrogen atoms are in different environments from the other two. This is confirmed by Raman spectra. 4 of hydrogen atoms are in different environment from the other two. This is confirmed by Raman spectra. Okay? Point C. This point C. C point. Only 4 out of 6 hydrogen atoms. Only 4. 1, 2, 3, 4 out of 6 atoms can be replaced by methyl group. CH3 or Me. Okay? Thus diborane cannot be methylated beyond CH3 whole 4 B2H2. This show the presence of two different kinds of boron hydrogen bonds. Therefore, the hydrogen atom which cannot be methylated are bridging hydrogen atoms. Okay, D point. Okay, D point. The terminal boron hydrogen are normal covalent bond. The terminal boron hydrogen are normal covalent bond with two electrons shared between two atoms. Okay. The terminal boron hydrogen are normal covalent bonds with two electrons shared between two atoms. These are called two center two electrons bond. 2C 2 electron. Okay. E point. The two bridge involve only one electron. So the two bridge involve only one electron from each boron atom and one from each hydrogen atom, making a total of 4 electrons. Thus the electron deficiency must be associated with the bridge group. Okay. Nature of bond in diborane. Nature of bond in diborane. Nature of bond in diborane. Okay, 1 minute. Nature of bond in diborane. Nature of bond in diborane. Nature of bond in diborane. Okay. The electronic configuration of boron is given as below. B5 is a 1s2, 2s2, 2p1. Okay. This is 3s. This is 2p. 1, 2. Okay. That 2s. Okay. 2s. That is 2s, 2p. Okay. Boron atom in excited state. Boron atom in excited state. Okay. sp3 hybridization. Okay. Lipscomb. Okay. Lipscomb 1963. Lipscomb in 1963 suggested semi-topological scheme for the structures of all the boranes. He explained the 3 center are banana bond of diborane B2S6 on the basis of hybridization. Okay. In boron atom and 2s and 3 2p orbitals of nearly same energy intermixed to form 4sp3 hybrid orbitals. 3sp3 in boron atom 2s 1 2s and 3 2p orbitals of nearly same energy intermixed to form 4sp3 hybrid orbitals. 3sp3 hybrid orbitals contains 1 unpaired electrons, while the last sp3 hybrid orbitals is vacant. Okay. 4 terminal hydrogen atoms, 1 s orbitals overlap with sp3 hybrid orbitals having 1 unpaired electron of boron atoms to form 4s sp3 sigma bonds, okay, sigma bonds, okay, and sigma bonds, BH, two center, two electron bonds, two center, two electron bonds, which are 4 in number. One s orbital of bridge hydrogen atoms overlaps with one half filled and one empty sp3 hybrid orbitals to form 3c2e hydrogen bridge bond, BHB. This gives a delocalized molecular orbitals covering all 3 nuclei containing one pair of electrons and form a bridge. This is a 3 center 2 electron bond. A second 3 center 2 electron bond is also formed. Okay? Okay. You can show as examples boron. Okay? Boron. Okay? Boron. Okay? Boron. This is bracket. Okay? HB. H plus boron, this is vacant. Hydrogen, okay. This is 2 empty sp3 hybrid orbitals. 2 empty sp3 hybrid orbitals. Okay, that is boron, okay, boron, okay, that is hydrogen, hybrid hydrogen, HB, okay, boron, okay, hydrogen, okay, R, boron, HB, okay, hydrogen, okay. This is overlap of sp3 hybrid orbitals from B boron with an s orbitals from hydrogen to give 3c2c bond, okay. Overlap of approximately same energy. Overlap of approximately same energy. sp3 hybrid orbitals from boron with and 1s orbitals from hydrogen. 1s orbital from hydrogen gives a banana shape. 3 center 2 electrons bond, which is shown. You can show hydrogen, boron. This is boron and This is boron, hydrogen, boron. Okay. Orbitals model of a three-centered bond delocalization of sp3 electron in boron. Okay. The delocalization orbitals of bridge are bent away from each other in the middle due to repulsion between the bridging. Due to repulsion between the bridging hydrogen nuclei. Hence, hydrogen bridge orbitals is shifted upward and the other downwards in the middle. Okay, the orbital models of three center two electron bond. You can show this. The shape of the bond is like banana and it is called banana bond. The sp3 overlap is a nose to nose and is called a tau bond. Okay, figure 40 you can show next figure. This is boron. Okay, boron. This is boron. This is boron, hydrogen, and hydrogen. Okay, this is 3C2E bond, B2S6 diborane, B2S6 diborane. Also, this figure is also represents the structure of B2S6 dark circular spot. This is dark circular spot. Dark circular spot represents electron of boron atoms and white spot. And white spot represents electron of hydrogen atoms. The two dotted loops. You can show. 1 minute. Sorry. This is boron. Okay. Boron. Boron, hydrogen, okay. Also represent this figure is also represents the structure of B2S6 dark circular spot. Represents electron of boron atom and white spot, represent electron of hydrogen atom. The two dotted loops represent a 3C2E bond which link up three atoms, two boron and one hydrogen atom, but in circular only two electrons are present. Thus, from the above discussion, it is clear that in diborane molecules, first point, there are four terminal boron hydrogen bonds. These are normal covalent bond, that is two center two electron bonds, and second point, there are three center bridge bond including boron hydrogen. There are three center two electron bonds. Both boron atom are electron deficient. Third point, both boron both boron atoms are electron deficient. Electron deficient. Okay. Next, higher borans. Okay. Next heading, higher boranes.